Okay, today I'd like to talk about this word that is really used a great deal in algebra, spell it correctly, that is factor. Right? It's used as a noun, it's used as a verb, and as a verb, we kind of use it for two similar situations theoretically, but on paper, they actually seem quite different. One seems much more complicated than the other, but they really are the same thing. So if you've already seen my videos recently, you have that definition written down, I hope. So factor as a verb, here it is. Okay. To factor means to rewrite a given number or expression as a product of whole numbers, usually excluding one, or expressions, meaning a product of expressions. Right? So we're used to seeing this for whole numbers, something like to factor 12. I can rewrite 12 as 2 times 2 times 3. There it's completely factored. Or sometimes we only want to go a little way. Let's say 12 is 4 times 3. Right? And the context of the problem will let me know whether I want partially factored or completely factored. Well, how do we get here? We kind of use division, but to divide, I have to start with one number or the other, right? Factoring means I need to think of, okay, what can I multiply to get 12? And that's what factoring expressions means as well. If I have something like 4x plus 10y, well, that's a sum. This says I want to write this expression as a product of expressions. I want to rewrite this not as something plus something else, but as something times something else. So how in the world do I do that? How do I use this factor as a verb when we're dealing with algebraic expressions? Well, it's really the same process that we use to factor whole numbers, right? I'm looking for, well, what can I multiply to get 12? Well, let's look a little bit at a time. To figure out what I multiply to get 4x, that's 4 times x. And 4 is 2 times 2 times x. And 10y, that's 10 times y. And 10 is 2 times 5 times y. Okay, well, that's still a sum. Well, let's think about what it might mean to multiply two different expressions. So before we finish this, let's actually start with the product, right? I know that 3 times 4 is 12, so going backwards, that's pretty easy. But if I have something like 3 times 5x plus 7, right, that's maybe less straightforward. 3 times something means I have that same thing added to itself 3 times. Exactly the same way that 3 times 4 is 4 plus another 4 plus another 4. And I can go by multiples of 4 fairly easily. 4, 5, 6, 7, 8, 9, 10, 11, 12, done. The multiples of this, I'm not just counting because of that variable in there, but I see this is all addition, so I can associate all of my x terms together. 5x plus 5x plus 5x. In other words, I have 3 5x's, 5, 10, 15 x's. And I also have 7 plus 7 plus 7. So I have 3, 7, 7, 14, 21. So the way we usually show this is not to explain how distributing works, but to just distribute. Take this factor and multiply by every term in the second factor. So the only work I would show for this problem is 3 times the first factor plus 3 times the second factor. There's my 15x plus 21, right? So all this writing in the red, I hope is a good reminder of why distributing works the way it does. But this process in the black is what I expect you to write on your paper if you're in my class, or what I encourage you to write on your paper if you're learning this for someone else's class. And this process gets a name, it's called distributing. Right? So we can put that as a formal definition here. Distribute. And to distribute means to rewrite a product as a sum, multiplying each term in the first factor. And usually our first factor will only consist of a single term, by each term in the second factor. And if we have multiple factors, 3 or 4 or 5 factors, that's going to involve multiple levels of distributing. But classically, this is shown if we have a times x plus y, we can say that's a times x plus a times y. Remember, variables are case sensitive. So capital A is a different variable than lowercase a. Right? Or if we have 3 factors, then I have ax plus ay plus az, and so on, right? It's a circumstance where we're using variables to show formulas to summarize definitions, right? So when I have 3 times these 2 things, I'm taking this only term by each of these terms. Right? Well, what does that have to do with this? Well, I'm trying to work backwards. I'm trying to get from this product to, from this sum backwards to the product. Right? I'm starting with the 5x plus 21 and trying to get back to the green expression. So let's look at how we could move this backwards, and then we can get back to the other expression. So if I'm starting with a 5x plus 21, I can recognize 21 as a product of 3 and 7. I can recognize 15x as a product of 3 and 5 and x. So now I can look at these 2 separate products and say, well, do those products have any factors in common? They do. This product of 21 came about by multiplying 3 times something. This product also came about by multiplying 3 by something. So I can kind of undistribute, I can factor out that 3 and put him in front. Right? I can factor this expression by finding the common factor of those 2 terms, putting that as a factor to be distributed, and then times the remaining parts on the inside. So let's apply that here. 4x, that's 2 times x. 10y, that's 2 times 5 times y. Are there any factors showing up in both of these lists? Good. Right, we've got a 2 here and a 2 there. Any other common factors? No, that's it. So my first factor is just the number 2. And my second factor is what's left here plus what's left over here. Do you remember me talking about the leftovers in a previous video? That's kind of a way to do it, right? So one way to talk about factoring to factor a monomial, which means a single term factor, right? To factor out a GCF of a polynomial, we're going to multiply the GCF by each leftovers. Right? Here's the GCF of these two terms here, 2, and here are the leftovers. So let's bring in some old friend numbers and see this in practice. So we earlier had looked at an example of 520 and 528. And we saw that the factors of 520 were, I honestly don't remember. So 528, I've got 4 2s, a 3, and 11. Then 520 was 3 2s, a 5, and a 13. Okay, so I've got 3 2s, a 5, and a 13 versus 4 2s, a 3, and an 11. So we saw that their GCF was these 3 2s. And so this other part is what's left here. So I can factor 520 as 8 times 65. I can factor 528 as 8 times 66. So this would be kind of silly to do what I'm about to do, but it illustrates the point. If I wanted to add 520 plus 528, I could just go off to the side and add it, right? But if I wanted to, I could factor this 520, 8 times 65, 528, 8 times 66. Recognize that common factor of 8. And inside, I'm going to put my 65 as the leftovers here, 5 times 13, and 66 as my leftovers here, that's 2 times 3 times 11. So this expression should be equal to this expression, right? All of these are equal to each other. Well, let's check that. 520 plus 528. 520, 528, pretty simple. 0 plus 8, 2 plus 2, 5 plus 5 is 10, so I get 1048. And let's look at this. 8 times this sum, 65 plus 66. 6 plus 5 is 11. 6 and 6 is 12, plus 1 is 13. So 8 times this sum, that's going to simplify to 8 times 131. And if I do 131 times 8, 8 times 1 is 8, 8 times 3 is 24, 8 times 1 is 8, plus 2 is 10. I get 1048, right? Same value. Now, if my goal was to find the sum of 520 plus 528, of course, just add it, right? There's no nothing to be gained by factoring out that 8. Now, there are some numerical situations where that might actually be a shortcut. Those tend to be fairly sophisticated, so if you haven't thought of it yet, I'm not going to require you to think through that. I'll just say it is useful sometimes just for whole number arithmetic. But where this really becomes important is in expressions like 520 x squared y. Let's make that y not look like an x. Plus 528 x See, leave it at that. There are lots of situations in algebra where seeing this as a product is going to be useful. So how do I do that? Well, I factor each of these. 520 is still 2 times 2 times 2 times 5 times 13. But now it's times x squared times y. So times x times y. 528 is still 2 times 2 times 2 times 2 times 3 times 11. But now it's being multiplied by x and z, right? We're starting out with the same process of fully factoring each term and then looking for what they have in common. 2 and 2, 2 and 2, 2 and 2. There's our old friend 8. I don't have any 5s over here. Don't have any 13s over here. But the next factor here is x. I do have an x over here. The next factor is a second x. I only had one. All right. Next factor is a y. No y's over here. Going the other way, I only had 3 2's, no 3, no 11, no z in this expression. So my GCF is 2 times 2 times 2 times x. In other words, 8x. And that's being multiplied by the leftovers. So what are my leftovers here? 5, 13, x, and y. Well, 5 and 13, I know that product, that's 65 times x times y. Over here, what are my leftovers? 2, 3, and 11, and also a z. Well, I know what 2 times 3 is 6. 6 times 11, that's 66. 66 times z. No one told me the value of z for this problem, so I'm just leaving it as 66 z. Both of these terms are being multiplied by the 8x, so I need parentheses there to show that this binomial, 2 terms, is being multiplied by this monomial, 1 term, right? So this patriotic expression here, red, white, and blue, is the factored form of this original boring black and white expression. We call the black one the expanded form, right? There are no parentheses. This is actually the simplified version. We call the red and blue expression the factored form, where the GCF is shown as a factor times all of this. Now, we don't usually put the dot here. I was being a little extra. So let me just write that one more time, the way you would write it on the test. 8 times x times this binomial. And that's how you factor expressions. You find the GCF of those two expressions. Usually your number is going to be a lot easier than these two. I just keep using the same pair for this whole section here. If you're jumping into the middle of things, just trust me that this is the prime factorization of 520. This is the prime factorization of 528. All right, let's do one more easier example here. Use our old friends 10 and 35. There we go. Can't get much simpler in this realm. So what is the GCF of those two? Let's make it slightly less simple. Let's say plus 21. There we go. Slightly less simple, right? So now we're looking at 3 terms. What is the greatest common factor of these 3 terms? Well, 10, that's 2 times 5. 35, that's just 5 times 7. 20, that's 2 times 10. And 10 is 2 and 5 times y. So what number is showing up in every list? I've got 5 here. This also has an X, but this does not have an X, this does not have an X. So X is not a common factor. Y only shows up on 1, right? 5 is the only factor showing up for all 3 terms. So 5 is what I have to put by herself outside the parentheses. And then I look for what's remaining here. I've got, let me change colors. I've got 2 and X. I've got 7. I've got 2 and 2. 2 times 2 is 4 times Y. 4 times Y is 4Y. Now, you notice the 10 was positive and the 20 was positive. So I'm only thinking of this as a positive 5, right? So this is positive. To get negative 35, I don't want to think of this as negative 5 times 7, because negative 5 is not the same as 5. I either want to think about it as just a minus, so this is minus and this is a plus, or think of it as 5 times negative 7, or this is plus negative 7 in the middle, and plus negative 7 simplifies to minus 7. Or the last way to think about it, which is probably usually the best way, is to factor out that negative as just a negative 1, and then the whole number factors, right? And if all of the terms have a negative 1 factor, sure, then we can factor out a negative 5. But if any of the terms are positive, especially if the first term is positive, then you're usually only going to factor out a positive GCF here and leave the sign of each term as it was, right? So here's our, not simplified, our finished factored expression, factored version of the expression. We start with a simplified version and unsimplify it by factoring out the 5 to get this. Okay.